Hi, in this video we're going to have part 2 of demystifying the big O notation tutorial. But before we dive in, let me introduce you to my Learning Data Structures and Algorithms course. It's completely free and it will stay that way forever. So don't wait any rule now to learn more. You will find a link to the course in the video description below. First, and before getting into the nitty-gritty details of this video, I would like to make a recap of the last video where we have introduced the big O notation. And we've talked about some related concepts. We started the video by explaining what's an algorithm. Then we moved to explain what makes a good algorithm, like how we can judge if an algorithm is good or bad. And for that we have given an analogy to illustrate this, which leads us to talk about the next point, which is why big O notation. Why do we need big O notation? Then we have moved to define big O notation, and finally we ended the video by providing the big O chart or the big O complexity chart. And concerning this point, we have said that we should always try our best to make our algorithm's complexity to fall in this region, the region of excellent to good to fair. Nevertheless, sometimes we might find ourselves in a situation where the complexity is O of n log n, usually referred to as the log linear complexity. But in most cases, we should always try to avoid being in the bad or the horrible complexity. In this second part of the tutorial, we're going first to deal with the two main types of complexity. Then we will move to have some examples on each one of them. Then we will move to big O calculation rules. Finally, we'll end up with having an example on how to apply those rules. Basically, there are two main types of complexity. We have time complexity and we have space complexity. For time complexity, it tells us how the execution time of an algorithm increases as the input size goes larger, and it is quantified relatively to the number of operations done by the execution of the algorithm. Same goes for space complexity, which tells us how memory allocation increases in relation or as the input size goes larger, and it is quantified through identifying the space needed for the input size plus the auxiliary space needed for the algorithm to run. In this first example, we want to say hi to the first person in a list of people. And if we analyze the function that says hi to the first person in the list, we see that it has got only one operation, and this or only one instruction, and this instruction executes like only one time, no matter how large is the size of the list of people. So we often say that this algorithm or the algorithm has a constant time, like a constant time complexity. So no matter how the input size grows larger, we have always a constant number of operations done by executing the algorithm. In this second example, we want to say hi to everyone in a list of people. So if the list of people is of size n, then we are looping over this instruction n times, which means that it gets executed n times, and the time complexity of this algorithm is denoted as O of n, which means that it increases linearly as the input size grows larger. This type of complexity is often referred to as the linear time complexity. In this example, we want to display every possible pair in a list of elements. For that, we have a nested loop here, or two nested loops, which means that this instruction gets executed n times n. Therefore, the complexity or the time complexity for this algorithm is denoted by O of n squared, which means that the time execution for this algorithm is proportional to the square of the input size, and we often refer to this type of complexity or time complexity as the quadratic time complexity. Now let's have an example on how to calculate space complexity. Let's assume that in this algorithm we want to print the sum of a given natural number n. So for this function we have an input n, which is going to take space of constant space of O of 1. Then we have a variable sum, which is an auxiliary space, and it's going to take O of 1 a constant time too, or constant space complexity. Then we have a function call here, which is also an auxiliary space of O of 1, and without forgetting here the variable e of the for loop, which is also going to take a constant space complexity over 1. If we sum up those numbers, we will have O of 4, which is going to be simplified to O of 1. So the algorithm complexity or space complexity is constant no matter how large is the input n. And we are going to see how to simplify the complexity of an algorithm when we reach the big O calculation rules in this video. Now through the following table I want to briefly mention some other types of complexity. We have the logarithmic complexity denoted by O log n. In this type of complexity, the growth rate of space complexity or time complexity scales very slowly comparing to the input size, and one example of that would be the binary search algorithm that we are going to see in future videos. Next we have the log linear complexity, which is denoted by O of n log n, and it sits between the linear complexity and the exponential complexity. And one example of that would be some sorting algorithms like the merge sort and others. Next we have the exponential complexity denoted by O power 2, and in this kind of complexity the growth rate doubles with each addition to the input size. One example of that would be the Fibonacci sequence. And finally we have the factorial complexity, which is denoted by O of factorial of n. And we can find this type of complexity in algorithms or problems that involves a lot of calculations of permutation and combination. One example of that would be the travel and salesman problem. There are some rules we need to follow in order to calculate big O. The first rule says that big O is always calculated for the worst case scenario. And the second rule says that we should add up the big O of each operation together with different terms for different inputs. And the third rule says that we should remove constants. And finally, to find the complexity of the algorithm, we should keep the big O of the dominant term and drop the rest. So to understand big O calculation rules, let's have the following example. First, let's start by finding the complexity for each individual instruction. So we have a constant time for the first instruction because it gets executed only one time, no matter how big is the input or how large is the input. Same for the second instruction and the third one. Now for this piece of code, we're trying to find x in an array 1 here, and printing its index. So the test here is happening n times, which means that the complexity is O of n. And we are considering the worst case scenario and considering that we are going to find x at the last position of the array 1. This operation is going to happen only one time, which means that the complexity is O of 1, or is a constant time. Now for the second part of the algorithm, we're trying to print all possible pairs in an array or the array 2. So for this instruction is going to happen n times n, which means, or p times p, because we have a different input here, so we should use a different term. So the complexity is going to be O of p squared. Now let's find the final complexity of the algorithm by applying the rules that we have learned. For the first rule is satisfied, since we are finding the complexity for each individual instruction at the worst case scenario. The second rule says that we should adapt those complexities we found with different terms for different inputs. So we will have something like the following. So if 1 plus 1 plus 1 plus n, this n plus 1 plus p square. This is by applying rule 2. So if we add up now terms, we will have 4 plus n plus p square. Now let's apply rule number 3, which says that we have to remove constants. So we will have something like the following. Now by applying the rule number 4, which says that we should only keep the dominant term. So the dominant term here is p square. So the complexity of the algorithm is going to be O of p square, which is an exponential time complexity. So this is it for this video. I hope that you've learned something new today. Don't forget to comment, share, like and subscribe to my channel. Thanks for watching and see you soon.